Okay, this is where we left off last time, right? Debugging. Debugging is most of programming. That's what you're doing all the time. Programming should just be called debugging. So don't feel like you're doing something wrong if you write code and it never works. That's what's to be expected. I even hesitate calling it normal because it sounds like I'm being like, oh, that's normal. No, like it is, this is hilariously, that's what this is. So get ready to be debugging. Don't think you're not good at it because you're debugging most of the time, because that's what you do. That's what programming is. Let's make sure I'm recording. Yeah, cool. Yeah. The benefit of debugging, though, too, is like, okay, why is debugging important as an exercise? Well, we got to make sure we are, like, if we're running our code and we're trying to fix it, like the process of going to fix the code is the learning process of programming. So that's where you're going to be doing most of your learning too. Like that's the slog you go through to pick this up. Because you got to really understand what you're doing. You got to really understand what you're, like what am I trying to do? What am I doing? Do those align? Do I understand my algorithm? Does my algorithm even work? It doesn't even work. Let's get that feedback. Let's see what works now. Right? That whole process, that's what it's all about. And yeah, so like beyond debugging what's good, well, it helps us improve important skills, knowledge of algorithms, knowledge of programming languages, the ability to reason logically, and the ability to reason about the flow and execution of your code. Sometimes the error messages that Python gives you are pretty helpful, right? Who's seen like a bug like this, syntax error, right? Of course you have. Now, these are bugs that are pretty easy to fix in the sense that like, well, like look, it's showing you. Like, oh, invalid syntax, why? Oh, the plus there, right? Great. Sometimes it might not be obvious, and if that's the case, you just copy the error message, throw it into Google, and it'll probably tell you what's going on anyways. But unfortunately, though, some of them are easy. Some of them are going to be quite cryptic. So, you know, that's where I do like the Google search thing. And to be honest, that's like if I get an error message where I'm like, I don't even know what this is telling me, that's the first thing I do. I copy paste it into Google and I see what I get. Common error messages that you've probably seen. Raise your hand if you've had syntax errors. Have you had indentation errors? How about name errors? Type errors? Index errors? We could do this forever, right? Because that's what this is, okay? Syntax errors, they're going to cause pretty helpful error messages. Now, not always. Sometimes you get error messages that are still a little funny. I see some people have them. Like, who here's had an error message where it's saying like the issue is here, but like the issue is actually up here? So it kind of like cascaded down. That'll happen sometimes, right? So you got to know like, well, it might not be right there. It might be a little bit before, but anyways. The message usually tells you where the error is, and sometimes it'll even like give suggestions on how to fix it, right? So there's not much of a debugging strategy for dealing with syntax errors other than just like, well, figure it out, right? Like, oh, I added a plus where to delete it, right? Like just do what it says. Now here's fun. Look at this code. How many errors does this code have? If I were to hit run, it will yell at me. But how many errors do you see here? So many. Well, I tried, like, don't yell it out loud right now, but like, look at them and try to like account for like everything that you see. Like, count how many you can find. Okay, how many have each of you found? Like you found 6? 7? You found 7? Okay, all right. You found 3?
I found 3, yeah.
Well, that's good. Well, let's see. Let's see what happens. Let's just throw this in and see. First, okay, yeah, that's going the wrong way. But in this particular case, let's take a moment and look at what the error is saying. And notice that it's actually kind of wrong. The error is saying that parenthesis right there was never closed. And although that's true, that's not really what the problem is here, right? The problem is that, like, well, I wrote the wrong one. I meant to close that one. So the error message is helpful. It was technically a little wrong, but there. Okay, cool. So that was one. Invalid syntax. Why is it mad now? Now here's an example of where it's saying the error is here, but it's actually not. Where is the error in this particular case, do you think?
To the left, where it says
Deaf. I spelled deaf wrong. My goodness. There. Okay, cool. Okay, that fixes that. Run. What? Well, I'm not asking you to answer right now. What are you doing? So I missed the colon. Why? Look, this is a perfect example of, like, look, you needed the colon right there. So here's an example of an exceptionally helpful error message. Invalid syntax. Oh, yeah. You can't plus multiply. What's this? Name broken is not defined. What are you talking about? I wrote it right there. Borkin. Oh my goodness, a typo. How many of you have had typos like this? And you're like, there's nothing wrong with it. What are you talking about? Yeah, this will happen a lot. And this is why I always say, like, when you're doing this debugging, go slow. Line by line. Never, ever, 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 ever assume anything about your code, because if you do, you can bet your ass that that is exactly where your mistake was. As soon as you're like, well, that's what it's called. Well, how is it? There's something wrong with Python. Python's broken. No, it's Borkin. There. And then, oh, name error, it's saying, oh, what the hell's walrus? Oh, yeah, that doesn't belong there. Or maybe I forgot to define it somewhere else. There. Now, I'm pretty sure I counted only 6. So you found 7? What was the 7th one you found?
I actually counted broken Borkin.
As to, okay, that makes sense. Okay, yeah. The mismatch, yeah. Okay, cool. That explains it. Awesome. There we go. Now it's fixed. Yeah.
So I thought for the walrus thing, I thought you could make a variable and not declare it, and then it would just be like, okay, well, this is variable. You can declare it later.
No. Now, I know you have some experience in Java, and in Java, you can declare before you define. But here, you got to do it in like one shot. Yeah. So you might be thinking your Java hat.
Probably,
Yeah. Cool. So any questions about that one there? Yeah, this is what you do, right? These types of errors, they give you some feedback on how to fix them. Sometimes, though, we have errors that, like, won't give you an error message. All right? Sometimes we have errors that will do what we tell it to. So, for example, we can mix types. Sometimes not a big deal. In fact, sometimes this might be exactly what we want, right? A, B, but A is an integer, B is a float. We can add them together and we get a float, right? There's nothing wrong with that. It worked. We can mix types. Sometimes it works, but Python can only do so much, right? Like, for example, here's one where we do get an error message, but it's because I'm mixing and matching types, right? 99 bottles of beer on the wall. You look at this and you're like, well, just concatenate the string. But Python's going to go like, well, 99 isn't a string. 99 is an integer. Maybe you wanted me to convert it to a string and concatenate it, but I don't really know. Python's going to be careful about how many assumptions it makes about what you want, because it doesn't want to start doing things you definitely didn't ask it to do. And you never told it to convert this to a string, right? So you got to be a little careful. Sometimes you get error messages, sometimes you don't. Like, is consistent or inconsistent, right? You look at this code. What's wrong with this code? Nothing, right? This code looks fine, all right? Now, if I go down here and I say, inconsistent 2 and 3, what do we get? 5, obviously, right? But what if, though, I do that input thing? We've seen this example a lot, right? We read input, and whenever you read input with the input function, what is the type of the data that you get? String. Meaning, this would give me 23, okay? Now, you can look at this and say like, well, you gave it the wrong type. Yes, but if you weren't paying attention, if you just read the input and you added them together like this, and you just forgot to convert it to an integer, that's going to be how it acts. So you got to be careful, okay? And here's why this could be very dangerous. Imagine that you have this set up such that like it's reading 2 values from sensors, okay? I didn't enter those values. Those values came from somewhere else, okay? It reads in the values and it prints out 23. And I go, okay, great, must be 23, right? I could only know this is wrong by like me testing it manually by going like, oh, give it a 2 or 3, I should get a 5. 23, what the hell, right? That's where I know it's wrong. But if I just deploy this and it reads from a sensor, I don't know what the sensor's reading, right? For all I know, okay, yeah, the sum of the 2 values from the sensor is 23. I guess so, sounds good, that's a reasonable number. But this could be a sneaky error that could cause a lot of trouble, as I hope you can see. Do you see why this is tricky? Things that we do to help, like what can we do in Python to help this? Can anyone tell me? And help is perhaps not even the right word, but what can we do? What have I been telling you to do? Type hints. Now, type hints won't fix this, but it's a way to encode information into the syntax, and hopefully it gives the user of your code enough of a, oh yeah, it's got to be integers, right? Hopefully. You could also maybe say like, well, just force it to be an int inside, right? Whether it's an integer, make sure it's an integer. Whether it's a float, make sure it's a float. But, like, okay, so like b equals int of b. There. This will fix it, right? Right? There we go. So even if someone accidentally inputted it as strings, it won't work. But if I do like this, it's just fine. Because converting an integer to an integer, whatever, doesn't make a difference, right? So we can see that works. But although this is a solution, it's a perfectly reasonable solution, there's this idea in programming, and this is more of like an advanced idea that you wouldn't really even talk about until like you're doing like software engineering. But there's this idea called like this, I think it's called like the substitution. I might be getting its name wrong, but like basically, there is in like the ideology of writing code, whether that you should always assume that even though this function was never intended to be used with strings, let's say I wrote this function, it was always intended to work with integers. There's a rule in software that like assuming this is a piece of software that's deployed, and maybe like Amazon owns this software and it's used like all the time, right? The idea is, even if the intention is to make this work for like integers, you should always assume someone is using it for the unintended reason, but it's still functionally correct. Meaning if you go and you converted it to like integers, now suddenly it's not going to work the way they expected it to because so you can create some like issues, right? But that's really outside the scope of the course. Yeah, so there's nothing wrong with this function, but what would happen, right? But 1 plus 1 is 11. Oh. And like I was saying, it may seem obvious, but if we're reading input from like a sensor and I don't know what those inputs are and I'm seeing a number 23, that's a very sneaky error. Because the error looks like it's right, like it's giving me the number 23, sounds reasonable. That's a number of the sum of two, that sounds right, but it was way wrong. And we wouldn't know. In fact, type errors are some of the easiest errors to fix. How do I word this? Type errors in certain languages, like Java, for example, which we move to next semester, it's not even possible to run your code with like a lot of the type errors. Where in Python, it'll run, it'll do what you told it to. So the type errors could be eliminated even before you hit run in other languages because of what's built into the language, but Python doesn't have that. All right, so yeah. And like, think of how easy it is to make this mistake. How many of you, especially early in the semester when you were doing kata stuff, how many of you forgot to convert the things to integers or floats or whatever, right? Like, yeah, you're gonna make this mistake all the time. But those are sneaky errors. Errors that it looks like it's working fine, and maybe it goes unnoticed that it's not. And this is also moving into like logic errors, where like, okay, I wrote my code, I hit run, it doesn't crash, it ran, but it's not giving me what I want, right? They are tricky to debug. These are the ones where you are the detective, looking for what's going on. And this requires you to get your hands dirty and figure out what's going on. And this is also where we start to talk about what strategies do we have to help with debugging. Logic errors. So logic errors, they're quite difficult to debug. Everything may seem to be working fine, but at the end of the day, something's wrong. Sometimes the errors may be obvious, like an infinite loop. Sometimes it could be like an edge case. Maybe there's an error in your code and you tested it 1 billion times and it seems to work, but maybe there's some funny situation where the inputs are just right that it crashes your program or something. Like, you don't know, right? So yeah, here's hoping you tested thoroughly. There are a few strategies that I could suggest to you for like how to distill where the bugs are. A few strategies are talked about below. Most people are going to develop their own coping mechanism, right? Their own way of debugging. Once you get enough experience, you end up having like a systematic way that you start to figure out how to debug. And debugging in that way really starts to like turn into more of an art than a science, where like you can show someone else your debugging strategy, but like, you know, you use your intuition and it works for you, so you know how to like kind of like finesse it to do what you got to do, right? So it's kind of hard to put it down into precise steps. You kind of know what you're doing, right? It's that intuition you develop. But just like everything else, you get better at debugging with practice. You're going to develop your strategies with practice. And also, like, it's common that like certain types of bugs will pop up a lot. So it's good to be able to recognize them early. We're like, oh, why is this happening? Oh, that happens because you had like an off by 1 error or something. Well, an off by 1 error is a pretty common error, right? So once you get familiar with it, you're like, oh, it's an off by 1 error. You like kind of know just by experience. Print. This is the simplest, tried and true method of debugging. I showed you examples of this before. If something's not working right, throw print functions into your code. As many as you want, it doesn't matter. Print out the value that should be 17 but is somehow 302 along the way in your code to see where something goes wrong. Like, oh, on this line of code it should be 14. Oh, it's not. Oh, well, the error's probably around here somewhere. So the prints are a really good strategy to kind of narrow down where the problem is. It's not always going to work, but it works a lot of the time. So prints are a great strategy. So like, yeah. Yeah, let's do this activity. You could have fun here, right? Take a moment, try this activity. Copy this code into Colab and throw prints in here to see if you can find out where the error is. If you can look at this and be like, I know where the error is, okay, great, right? Fantastic. But if not, that's fine, that's normal. Throw in prints to see if you can figure out where the error is. I'll give you a few moments for that one. Did you find it? Good job. Raise your hand if you found it. Raise your hand if you'll find it and like, just come on, just give me a minute. Okay, I'll give you a minute, yeah. Keep hunting. All right, here's how I'd go about doing it. I'd first start with like, well, look, all I know is that there's an issue here. The way that we're doing these tests, it doesn't tell us why it's wrong, it just says that it's wrong. So what can I do? Well, let's just call this function and print. What does it give me? Well, it gives me 15. And obviously, by the way, if you're doing this, you can't put it down here because this won't give you anything. Why? Well, the program crashes on line 10 by design. So if you want to know what it is, you got to put it before. So the answer is 15, but it should be 10. Okay, clearly there's something wrong. Now, look, I know that based on what this function's supposed to do, it's supposed to sum up the numbers from like 0 to n exclusively, meaning it doesn't include n, right? So it should be 10, right? Because 1 plus 2 is 3, plus 3 is 6, plus 4 is 10, right? And we don't include 5. But if we include 5, 10 plus 5 is 15. So chances are it has to do with like an edge case situation, okay? So I probably included the 5. So I immediately go in here and be like, okay, well, that's interesting. Because I would look at this and say, well, if it was including the 5, I would expect it to be c is less than or equal to n, right? Because then it would have included the 5, but it's not there. So that's interesting. Did n get changed? It shouldn't have, but let's just check. Print n. No, looks fine to me, right? And you might be like, why do we see all those values? Here, let's go to this one. Maybe it'll be more obvious. Why do we see 0, 5? Well, the first time through the loop, n is 0. Next time through the loop, it's 5. So there's nothing wrong with n, at least not there. Okay. Okay. Well, print c n total. Let's say. Okay, well. Okay, perfect. Now I think I can start to see the problem. Okay? Because this makes sense, 1 and 1. Once I'm done this, first time through the loop, 1 and 1, that makes sense. Why? Well, because 0, 0, okay, we add 1, and we increase the total. Next time, 2 and 3, yeah, and then 3, 6, yeah, it keeps going. But again, I'm seeing, why is it running for 5? It's running for 5 for 15. What is going on? Okay, look, if it's not there, okay, well, let's move the print there. I don't know. Is that really going to make a difference? Okay, that's good, because now I see what is C before I add anything to it. Oh, I see the problem now. It's that the first time through the loop, before I add anything to total, C should be 0. It's 1. How did that happen? I'm incrementing C before I add it to the total. So like for example, it's 4. 4 is less than 5. Increment it. It's 5. Add 5 to the total. There's the mistake. So we were using prints in this iterative process to kind of like figure out where the issue is. So the solution here is, well, don't increment C before. Yeah.
I did it a different way.
How'd you do it?
I just put, well, C is less than n minus 1.
Yeah, but that didn't fix the problem.
No?
That, you put a Band-Aid on, like, maybe that's not the right way to word it, but like, that really isn't, the problem still exists. It's not like, well, really the issue was there. Now, did that fix the problem? Yeah, but now your code is really like, detached from like what it's like what it means. Yeah.
I also did it a different way, but I feel like I did it wrong and just ended up getting the right answer.
Well, what did you do?
I took total plus equals C, took it out of the while loop, and then just did total equals C plus n. And
Yeah, that probably wouldn't work. Put in like the number like 10. That adds up to 55, I think, right? It gave you 20?
Yeah.
Is the sum of the numbers 1 through 10 20? No. So yeah, you just, and that's actually why you got to be careful, because you need your function. This is a funny thing, right? You've got a function, right? You plug in a value. You want it to map to the correct value every time, right? For all of them. You just happened to give it numbers where, like, the function's wrong, but on that input, it gave you the right answer, but on everything else, it'll be wrong. So yeah. And by the way, people were asking me, this goes back from like earlier in the semester, people were getting like mad and they were saying, well, you know, on Caddis, it's just saying it failed, but it didn't tell me why. It didn't say like, well, it failed when the inputs looked like this. So how can I fix it? That's the game. Because if you knew what all the test cases were, imagine like, oh, input 1 is going to be 1. Well, then and the answer in that case is supposed to be like 77 or something, right? And then input 2 is 14 and so on, right? So imagine there's some like general function that's like the right one, but if you knew all the inputs to outputs, you could write a function that maps all of the inputs that it's going to give straight to the outputs. Like if x equals 1, return 77. If x equals, and so on, right? Which is clearly not some like generalized function. It'll break as soon as it gets something it doesn't see. So that's why we can't, because it's too easy to cheese at that point. Alrighty, okay. So the process of debugging with print typically follows like what we just saw. You generate like a hypothesis. Well, this is how it's supposed to be acting. Add a print for that variable, hit run. Is it what it expected to be? If it is, chances are the problem's somewhere else. If it isn't, well, you're onto something, and follow that until you find it. Each print enables us to form a new hypothesis, assuming we need to, right? And depending on the complexity, you might find you need a lot of prints in order to make it work, and it might take a lot of time. And don't always just be like worried about printing out values. Sometimes you just want to know, did a chunk of code run, right? Like imagine I did this, right? Right, like I had that typo, okay? And I'm hitting run, and it's wrong all the time, right? And I'm just like, did I run? No. Oh. Right? So this while loop definitely should have ran, at least based on what I think. And so I just threw a print in there. Did I run? No. Uh-oh. So this loop isn't running. Why isn't it running? Oh, I got it. Okay, here we go. Right? There we, okay, cool. Now I'm good, right? So it's not just about printing out values, it's also to give you an idea of flow. Did your program even get to where you think it does? That's also an important aspect of this. Okay, yeah, each print, yeah, okay, cool. Pencil and paper. Never, ever, ever, ever make assumptions about what your code is doing. I know I just said that. I gotta stress it. Never assume. Because as soon as you're like, well, those 2 lines do this, so clearly no issue isn't there. Yeah. Chances are that's where your issue is. You're always like, the issues happen where you make assumptions. Your code isn't working already, so why would you assume any part of it's working, right? Like, oh, those 2 lines do this. Does it? You don't know. It's not working. Maybe something's wrong there. So one of the tricks is never make assumptions about what you're doing. Do not assume a variable has a specific value. Do not assume any specific functionality of any chunk of code, whether it's a function or maybe like, oh, the loop, oh, this loop iterates over. What does it actually do? Never assume. This is easier said than done. I say this, and I do this all the time. I'm always assuming, well, this is how it goes. It's a foolish thing I do. Everyone's going to be doing this, but try to resist the urge, okay? So a workaround is to don't actually run the program. Look, you've run the program, it's not working. So you run the program. Grab a sheet of paper and execute the code line by line without making any assumptions. That's always where you're going to screw up. So don't. What does each line do? And why do you need the piece of paper? Well, chances are you're going to have a couple of variables that are changing their value, right? So you need to keep track of them, right? And visualizations always help. But that strategy works really well. But no one wants to do this one because you feel like, no, it's slow. I'm smarter than this. Stop. Stop wasting your time thinking you're smarter than you are. Programmers are stupid. That's why we can only do one thing at a time, right? That's why your code isn't working, right? So look, slow down. This works pretty well, okay? So consider actually doing it. One of the best investments I got back when I was an undergrad, this was like before tablets. So if you have a tablet, you're in luck, great. But like I bought like a little whiteboard for my room, something like this, and that's where like I was able to kind of like do everything, right? So that was great. I didn't waste paper all the time. Yeah. Yeah, so yeah, keep a piece of paper, execute the paper line by line. The benefit of this approach, it slows you down. It really slows you down. And because like you're not running it on the computer, it's a little easier to not make assumptions, although it's still easy to make assumptions. Because you look at a line, you're like, well, what does that code do? Well, okay, it's going to add those. Does it? What does the code say? And it requires you to be very like intentional, very deliberate and thoughtful about what you're doing. This may sound tedious, and it can be, but if you do it right, it's probably going to work for you pretty well. Yeah, okay, yeah, so the point here is to take your time and think about every line of code. Every single line, right? And if your line of code is doing more than one thing, then you better make sure you're keeping track of everything that one line is doing. And I don't recommend having your lines do more than one thing, right? I'm a big proponent of like one line does one thing most of the time in general. Rushing through doing something like this is never going to work. You are defeating the purpose of trying the strategy. So when you rush through it and start making assumptions, you are inevitably going to fail because that's where the errors are in the first place. You're here because your program is not actually doing what you want it to. It's going to be rather silly to use your incorrect assumptions about what your code is doing to run the code yourself because you're going to be wrong, obviously, right? So don't make those assumptions. Then there's delta debugging, which I believe you kind of talked about before. This is the idea of like, well, you've got your code, comment everything out. Just get rid of it all. You don't have to delete it, just comment it out. Run. Okay, cool. All right, cool. Add one line in, run. Is it working as intended? Cool. Add another line in, run. And so on, and so on, and so on. That's also a pretty good strategy, right? You're also going to be like, you're going to want to do like no more than like 1 or 2 lines at a time, and you're probably going to want to make use of like prints to see like, okay, is it doing what it's doing, right? If a line is added and then suddenly it's not doing what you expect, you're probably on to something. If not, well, keep looking. If you remember from like a month ago when I was talking about like that, remember that like putting things together lecture where I started talking about like, okay, how do you go about writing like bigger pieces of code? And the answer was, there's no answer to this. There's a lot of different philosophies on the best way to do it. But one of the ones I recommended to you that works really well at this stage is start with an empty function. Add 1 line of code. Assuming you have an algorithm in mind, add 1 bit at a time and hit run. Add 1 bit, hit run. Add 1 bit, hit run. This is the same idea here. Has anyone ever heard of rubber duck debugging? This is a good one. This is shockingly effective. It's a real thing too, by the way. There's a wiki page and everything. Right there, right? What do? You get a rubber duck and you explain to your rubber duck what your code is doing. How could this possibly work? Because when you are like vocalizing what you're doing, you have to do it slower than just thinking about it. And the number of times that you go like, well, okay, first this line of code does blah, 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 and then the next line of code does, oh, no, it doesn't. I see. As soon as you slow it down and you start having to like explain it, it works. You don't have to use a rubber duck. You could use a teddy bear. You could use your mouse. You can use your grandma, whatever. Your grandma's probably, maybe she's a pro, I don't know, but if she's not, that's not the point. The number of times me and my buddies, all I needed was someone to talk at. I don't expect them to give me any insight. I've been working like for years on this project. What are they going to show up and be like, here's your problem, right? Of course not, right? But all they needed to do was just listen to me. Because as soon as I took the chance to kind of like speak about it, oh, this is what the code is doing, there you go. So this actually works. So any question about these debugging strategies? Now, the point here is not like, oh, you should go do this or this or this. This is to just kind of like say probably what you already know. You probably already knew about like, well, yeah, of course, delta debugging. Yeah, obviously that could work, right? But yeah, that's a common strategy. Throwing prints in there. Yeah, that'll probably work. It's good, but it's a common strategy. Great. The pencil paper, common strategy. I'm not telling you, oh, you need to do the pencil paper strategy. You need to do delta debug. That's not my point. My point is have these in mind. Next time you're faced with a bug, try to keep in mind what are common strategies and then develop your own strategy for debugging. So, I know I asked last time, but I'm going to ask it again. What debugging strategies have you been using so far? You've finished assignment 2, presumably, so like at that stage, yeah, you're going to be encountering bugs and you're going to had to have figured out where are the bugs. So what did you do? How did you figure them out? Who's got some, like what did you do?
I use the delta debug. That's what it's called for the couple of functions.
Yeah, it works, yeah. And did you throw prints in there to make sure where things were doing?
For the like the infection ones, like the cure.
Yeah. What else? I know you mentioned delta the other day.
I'm sure how to categorize it. It was pretty small, but one of the biggest things that was bothering me for way longer than it should have is I put the return in the while loop by accident. Pretty small, but it took an embarrassingly long amount of time.
But that's debugging. Debugging is like it's only obvious once you know what the problem is, right? So you can be like, oh, I should have saw that. Well, you didn't, and that's not because you're stupid. It's because like it's hindsight, right? I mean, we're all stupid. We're stupid programmers, right? Programmers are dumb, but it's all about how we cope with it. What else have people tried? I'm willing to bet people in here have used pencil and paper in some way to help figure things out, especially like on Caddis. I've seen people with that, right? Kind of like working out what's going on. Well,
Kind of did it with, like I would have another program open, and like running an error, just like not pencil and paper, but it's kind of like that way.
yeah, same idea, right? Like you're kind of like keeping like a log. Yeah. Cool. Yeah. So everyone develops their own strategy, and so just don't worry if you're not there yet. Yeah, it just comes with experience. I could give you as much advice as I possibly could. At the end of the day, you're going to kind of develop your own strategy. In the same way that you kind of develop your own strategy for writing code in the first place, right? I give you all the tips and tricks imaginable, but you got to just find what works for you. Yeah, cool. Okay, file I/O. We know how to get information from a user. We know how to store variables and data. We know how to manipulate data. But, like, look, think back to the Starbucks assignment. Imagine that someone had to sit and enter every latitude and longitude. How long was that Starbucks file? 25,000. No one's going to do that, right? That's insane. Fortunately, we can read files, right? So that data can exist in a file, we can read it in, and now we can process massive amounts of data like that, as opposed to like entering them one by one. Which fortunately, yeah, if you did assignment 1 right, one of the first steps was read that function to load data and try to get a sense of what the hell it's doing. At that stage, you probably didn't quite understand a lot of what was going on, but I'm willing to bet that if you went back now, you'd probably have an easier time figuring it out by virtue of like the loops and knowing what those are in lists, right? Cool. Text files are a great way to store text data. Now, what is a text file? Turns out a lot of people these days don't know. A text file is a super basic file. Okay? Like Notepad. Just open up Notepad. Great. I've got Notepad. Okay. This is stuff. I love text files. It's just text. Great, that's it. It's very simple. It doesn't have any fancy characters in it, right? It's just, there we go. It's a text file. Awesome, right? It's just text. There's no bells and whistles. It's not like a Microsoft Word document or anything. It's just text, okay? I can save this. If I save it to my desktop, it wants to save it as a .txt, okay? right? So there we go. This is stuff.txt. Great. I know it's a text file because it says .txt. Now, by the way, technically, the file extension doesn't really matter. The file extension like helps your operating system know how to interpret what that file is. But like I could try to open this file in like a picture viewer and it'll try, it just won't work, right? So like just as an FYI. Also, this is especially true if you're on Windows. I'm not 100% sure on Mac, but warning. And if you are on Windows and you plan to take more computer science, listen carefully. You're going to want to go here, I think it's under here, Options, View, the default, I believe, is this is on Windows. You don't want this on. It's going to create nightmares, I know from experience. The default is it'll hide the file extension for common file types, okay? But if that's on, you would only see like this, and then you might be confused, like, oh, what is it? It could get confusing. So if you're on Windows, I highly recommend don't hide the file extensions. Anyways, okay, cool. A text file. It's just a text file. It's just text, right? They typically have a .txt extension, but it doesn't really matter. Most of what we are about to see will work with many different file types, not just text file. It'll work for a lot of basic file types, but I'm using text because it's pretty straightforward. There are a few ways to load data from a text file into Python, but because we are basically out of time, we've got 3 minutes left. That's not enough time to sink our teeth into this. We'll stop here so we could start here on Friday. Any questions? If you haven't noticed, assignment 3 also has a due date. It's the 3rd, I believe. The test is on the 5th, I think. Let's check. Tic-tac-toe. Yeah, November 3rd is the deadline, and the test, I believe, is the 5th, right? Is that what I said? Yes, perfect. It'll be in class. It's going to be a very similar format to last time. Obviously, just the best way to study is to practice. Assignment 3 is going to be darn good practice for the test, so, you know, that's why I want it due before, so, you know, you've done it. Cool. All right, I'll see you all later.